Good morning. Simple announcement. Assignment 4 deadline is this Wednesday and assignment 5 deadline is next Wednesday. I still haven't decided what to do with the midterm. So if you have any comments or any idea, you're welcome to send me a direct message just to me here, and I will consider them when I make decision. Okay, so of course the situation is very dynamic. So face to face is impossible, and it will have to be online. And this kind of online exam has to be well, according to my previous experience, I will require you to be it's a closed book exam. I would need you to set up your environment properly, and I want to check everything. The reason is not because I want to create pen for you. I just want to be fair. I want to have an assessment which is fair to everybody. And of course, this is never pleasant. It's not pleasant for you to be watched, and it's not pleasant for me to watch you either. Okay, so this is one option on the table. The other possibility is to cancel the midterm and shift the score to the final. That's also on the table. Okay, so if you have any view, please take these 2 minutes and send me a message now. Okay, it's really right now is well, you can see this as brainstorming. And if you have other creative idea, as long as it's fair and reasonable, I'm willing to consider them. And in particular, if you know what other courses are doing, you can also let me know. I will consult the teacher. For example, if you see a particularly nice arrangement that you like, let me know. I will consult the teacher. Okay, so please, your feedback is needed. Okay, more. Okay, there's one comment saying that prefer to change the midterm to an assignment. That is not something I will consider all this, but I have my concern because I have no way to make sure the midterm the assignment is really your own work. So as I say, how to conduct a fair assessment is always a priority. And another scenario is this: it's very difficult to arrange for this kind of midterm, and we can only realistically arrange for one. And if we do this, we will put in a lot of resources, and if you cannot come, and we will not really be able to offer makeup, then we will still have to shift the score to the final. Okay, so this is one possibility people should keep in mind. Okay, more. I don't think we should spend too much time. Just again, I want to hear your thought. Okay, now maybe some of you didn't get me, or maybe you show up late. The face-to-face exams are almost impossible. So everything has to be online. And when I run online exam, usually in the past, I really did it myself using a lot of resources. I get my research students to help. So we are very strict about this. So that's to say you need to follow the protocol, our protocol. Okay, and it will be online, and then you think about whether this is practical. In any case, final, I guess, will be the same. So you still have to face the online version. I'm sorry. Okay, one question is if you cancel the midterm, can you shift some score to assignments? This is possible, but not much. So right now, assignment is 20, final is 50, midterm is 30. So if we cancel the midterm, I can shift 10% maximum to assignment. So it will become 30% assignment and 70% final. That's the best I can offer. If I do much more than that, I think it will be difficult to get approval. The reason I'm confident that 30, 70 will work is because I did it before. So I can just say, okay, 2 years ago, it was 30 and 70. So it was approved. And there's no reason why this time it won't be approved. That's, again, from operating from the confidence limit. Everything needs to be approved. Okay, any more? Again, sorry. Listen carefully. The next question is this: will the final be face-to-face? As I say, I don't know. I cannot predict what will happen. But the midterm most likely will not be face-to-face. Almost impossible to be face-to-face. Midterm will be online. Final most likely will be online, given if you look at how the situation in Hong Kong is right now. Okay, so final, we can decide later. We might have another discussion like this, but my priority is what should we do with the midterm? And of course, I can decide by myself, but I want to hear your opinion. And indeed, thank you for those of you who send in comments. Okay, so I hope there's no misunderstanding that the midterm has to be online. And I understand the university has already changed the final to be online as the default mode. This might be, maybe we can override this later if people really want to meet face-to-face. But we need, right now, as of today, if I want to request for face-to-face exam, there are a lot of paperwork for me. Okay, so please understand the situation. A lot of paperwork means I need to justify it, and then I need to give a proposal on how to ensure the safety of everybody. Okay, the next comment. If final is also online, it doesn't matter too much whether we have 1 or 2 online exams. This is a question about time. Okay, this comment, the question is about time. I believe and I hope by the time we have the final, the situation will be more predictable. Okay, and right now is my concern is the situation is so dynamic, and all these online exams are synchronized. You need to come on time. So suppose you are committed to the online exams for the midterm and you cannot come. What should I do with you? That is another issue. You cannot come, maybe because of the reason that is beyond your control. Okay, so that is right now I'm inclined to run 2 exams, just like what you mentioned. It doesn't matter from my point of view, but can everybody come? That is a question, and it doesn't matter from your point of view, but it does matter from our point of view, from the teaching team. How do you ensure? How do you run this exam smoothly? Because we don't have resources from university anymore. Everything is down to us. We have to run everything ourselves. In the past, for final at least, I just need to give the exam paper to the university, and then I don't need to do much. They will run it, and the answer book will come to my office, and I just have to grade them. And right now, I will have to set up a lot of computers to monitor. So it's not pleasant for you, and it's not pleasant for me. So let's at least we should reach this kind of understanding. All right, so more comments will be read, but let me start the lecture today. And thank you for your input. And most likely, I will also run out of time today because of this. And as usual, you can leave if you need to, but please watch the video. Okay, so let's start the thermodynamics. It's more interesting and less depressing than this online exam arrangement. Okay, so here we go. This is a quick recap that we will need today. So you already saw this, and now today I want you to keep in mind this line here. When do we minimize the Gibbs function? So we minimize the Gibbs function when we have this condition of T and P as the control parameter, which you can set constant. Okay, so in this case, this is the case. Okay. Sorry, this university life online, I also don't like it. That's why at the beginning of the lecture, at the beginning of this course, I told you the time we are able to spend together in that classroom in Science Center is precious. So there is I don't like it either. It's an educational disaster. It can be any time. It's not necessarily just semester 2, but semester 1 was very pleasant. I managed to give the entire course face to face. It has been a while since I managed to do this. Okay, so sorry, still coming back to thermodynamics. Okay, this is something we will need today. Okay, so last time we talked about this TDS equation. I gave you 2 versions, and this is the standard version, which we write it in terms of this kind of partial derivatives, and then we derive. I derive one for you, and then you can try to practice how to do the other 2. Okay, and then I also changed all these partial derivatives into something we defined back in lecture 1 or lecture 2, long time ago. That is, we changed all these partial derivatives into beta and kappa. Okay, the definition of beta and kappa are shown here. We will be able to talk about compressibility and thermal expansion. The reason of making this change is to really remind you that everything on the right hand side of these equations, these 3 equations, are experimentally accessible. Okay, so that is one thing. And the second thing is, once I change to here, I know how to obtain beta and kappa for an ideal gas. Right? We did it before. Again, it's back in lecture week 1 or week 2. And therefore, we can plug it in and see what we get. And this is what we did. We look at sorry, this is the slide I copied from last time. So we look at TDS1, so TS1, TS2, and if you do it properly, properly, I think the key step is this one, this du. How do you manipulate this du? If you do it properly, you get your first law. Okay, and if you do the same thing for TS2, you also get the first law, but you can argue that that is first law, but it's written for dH, enthalpy. Okay, you get a corresponding result for the enthalpy. So of course, the fun thing to try is what happens to TS3. Can I get? We just play. We just play and then see what we get. It's a way. It's not really a proof, but it's a way for you to see that things really work properly, or everything is nice and consistent. So let's try that. So that is here. Here. So TS3. Okay, so let's try the try to play with DS3. There are many things we can do, but I would do one spatial thing here. So DS3. Okay, what do we want to do now? I want to look at the case when we have an adiabatic process. So it's just I choose to play with this. Okay, you can do something else. So I'm going to look at an adiabatic process. Look at an adiabatic process. Okay, you change from state 1 to state 2 via an adiabatic path. Okay, and in this case, I claim that ds has to be 0. Okay, now this one I would write here. So in this case, ds has to be 0. Now all this requires thinking. Okay, why? I think it's probably not difficult for you. Okay, I'm going to write the result. So I'm going to take this line here and set the left-hand side to be 0. Then I can just evaluate right-hand side and you will see what we get. So I will have this kappa divided by beta. And kappa is 1 over p. Beta is 1 over t. So this I will have t divided by p for this term. And then I have dp plus cp. And then I have 1 over beta is 1 over t. So I have t divided by b dv. Okay, nice. Okay, so I don't need t anymore. T cancel. So what I have then is I will have CV heat capacity, and dP divided by P is log. Sorry, log P plus CP log V. Sorry, D log. Sorry, D log V. Okay. And now you probably already see something you know before. So there's a D here. D. Okay, so I will have this adiabatic process. I will have D log P is minus Cp divided by Cv D log V. And what do we call this ratio? This ratio is our adiabatic constant, right? This is the ratio of heat capacity. Okay, so now I integrate. I will just integrate from state 1 to 2 on both sides. Okay, so I will have log D log minus 1 to 2 gamma D log V. From here, you have seen it. You have seen it in chapter 3, I think, when we talk about first law, right? And you get a log of P2, pressure of state 2 divided by pressure of state 1. And here we talk about volume. So you have minus gamma log of V volume of state 2 divided by volume of state 1. Okay, rearrange, you get the desired result. You get PV to the gamma is a constant, which is what you learned before. Okay, so if I ask you, how do you get this result? Now you have seen the second case, right? You have seen it once a long time ago, and this is the second way you can get it. The first time you saw it not so long ago, in chapter 3, we really use the first law, and then we look at the heat exchange term, and then we look at the work done, and from there you look at the ideal gas. There's that main result, how to write the change of the internal energy du, right? For the ideal gas is simply a CVDT, right? So from there you get this result. So this is the second way to get it. Okay, so now I want to take this chance to maybe to remind you. I don't know whether you have seen it, but I will give you another way to do this. Okay, so this one, this is the third way. This is an aside. What else can you get this PV to the gamma is a constant? So in preparation for statistical mechanics, we can start to do things a little bit more specifically. So what do I mean by this? So now I assume something, assuming that somebody, your friend, your theorist friend, your experimental friend told you this. I'm not asking you to derive. I'm saying you are given this. Suppose you know the internal energy of your ideal gas. Okay, this is a result which you might have seen somewhere, maybe in 2041. You derive this probably, or elsewhere. Okay, so that is to say, you know the internal energy of your gas is given by this. And this is a very specific case. We are going to come back to this case a lot when we do our statistical mechanics. So the preview is this. This is, you see this 3/2? This already tells you something about the gas. So this 3/2 means this gas only has translational degree of freedom. So that's to say, we have this thermodynamic system, which is a monatomic ideal gas. So I cannot have a diatomic case, because if I have diatomic case, my internal energy will be different. There, the two atoms in the molecule can vibrate. I imagine there's a spring connecting them, and they can even rotate about their central mass, so they will have more ways to store the energy, and this will not be the case. Okay, so this is a simple case. Just think of them as non-interacting point particles. Okay, so from first law, I know I can write du is d bar q plus d bar w. Okay, I look at an adiabatic change, so this is 0. And more importantly, if I want to write, if I have a piston cylinder system, which I want to be able to write this next line here, this means this process has to be reversible. Okay, that's to say, if I look at the reversible process, I can go from all the way from the left to the very right, and this should also help you to answer my question why in the TDS equation I set ds to be 0. Okay, so this is a chain of argument which we need to follow. Okay, so this I can hopefully I can get it done very quickly. I just want to rewrite this a bit. So this is 3/2. It's an ideal gas. I know how to write NKBT. This is just PV. Okay, so I use this equation. Now I look at what? I look at 3/2 PV. And I have minus PDV. Okay, now I do the differential with using the product rule. I will have PDV. I will have plus 3/2 VDP, and then I can move this to the other to the left hand side. I will have this. Okay, so rearrange. I will have PDV. So I have my 5/2 PDV, and then here I have 3/2 VDP. Okay, and now you see your log again. So I will have my dV divided by volume is the same as minus dP divided by P. Okay, so then I just need to make sure I have the correct constant here. Okay, and I integrate from 1 to 2, from state 1 to state 2, I get the same result. Okay, so this is the third way. Once you know a little bit more about your ideal gas, you will be able to get this result. And this is less general. The most general one is the one I did back in when I introduced the first law. And of course the one I showed earlier today. Okay, so here when you see this kind of number, it means I already know more about my system rather than just assuming this is a simple ideal gas. Okay, so this is the result. Okay, last thing I want to talk about before closing this chapter is this. I want you to, this is the chapter which we learn Maxwell relations. And at this moment, this is also very a good place to talk about this assignment problem you did before. So this assignment problem asks you to show the difference between the heat capacity. Okay, so this difference is written like this. Okay, so I just reminded you about the definition of beta and kappa, and you just learned about Maxwell relation. Okay, so can you use your new tools to show this quickly? Okay, so I'm going to present a way to show it. This is actually the method used by Blunder and Blunder. I think it's very beautiful. So let's have a look. Okay, so you can write entropy like this, right? The entropy, the change of entropy can be driven by the change of T and V. Okay, so write this down in symbol. I will have this dt plus dv, and then I have this. Okay. Now, the reason I want to do it here is because I still want you to remember how to manipulate partial derivatives. So now there is the next step. I think the only thing is the next step, just in case you don't understand Blunder and Blundell. So I'm going to explain here. So what I'm going to do next is I'm going to evaluate the change of all this differential with respect to temperature. Okay, so that is to say I'm allowed to do this division, right? I can divide by dt, but you should not think like this. You should think like I'm going to let all this change with respect to t. That is to say I have another control parameter that will influence dt, dv, and df. Okay, so once I do this, because this is equality, so I will have to use the same parameter for both. So I choose this to be T, to be the temperature. Okay, so this is a coefficient. Just imagine this to be already a constant. It doesn't change anymore. So I will have to only look at the differential. And I have dt divided by dt, so dt is gone. And then here I will have, again, this differential. Just think of it as a coefficient which we don't have chance to manipulate. And then I'm going to look at this change driven by the temperature. Okay, you have seen this before when I talk about this meaning of partial derivatives. When we have face-to-face, I gave you that puzzle. So if you are not comfortable with this line, you go back and look at that puzzle and the solution of that puzzle. Okay, and now I have to answer the question, what do I want to keep constant? Okay, so mathematically, I have the freedom to choose what I want to keep constant. I choose to keep pressure constant. Okay, why do I want to do this? Because then I can generate my heat capacity at constant pressure and the heat capacity at constant volume very easily. Okay, soon I will get this result, right? This is manipulation. You have other ways to do that, but this is one way. Okay, so how do I get Cp? I just multiply by T. That will give me the definition of heat capacity. Okay, because this will give you d bar q dt. Okay, so I multiply by temperature, and immediately I get my Cp. Move this term to the left. I have Cv, and then I have T. And this. Now, what is this? This is a change of volume when I change the temperature. So this is at constant pressure. This is isobaric. What is this? This is thermal expansion, right? So thermal expansion is defined here, right? Okay, so I will have beta times volume, right? So this one is beta times volume. This is beta times volume. This is the definition. Okay, I already get my volume, my temperature, I have my beta. So I'm there's one factor of beta divided by kappa missing. And that has to be here. Now we know it has to be there, but we better show. Okay, so this one better be this missing factor if my proof is correct. And how do I do this? Now you know Maxwell. Let's use Maxwell. What is this? This is one of the 4 Maxwell relations. Okay, so this is actually this partial derivative. Okay, so you have P at the top, V at the bottom on the other side, and then S times T. Okay, and this one turns out to be this ratio. This I don't want to spend time to prove. This is something you did, and I gave this note before. Okay, how do you do that? Reciprocity theorem. Okay, and done. With this, I basically get the result. Okay, so I get Cp minus Cv, and this is Tv beta squared divided by kappa. Okay. All right, so this is what I want to say for this chapter. And then I want to invite you to read, there's some comments on how to use all these tools. What are the some tricks that you can use? What are the tips that you can use? And those are near chapter 16. The end of chapter 16 in Blundell and Blundell. Okay, it's 2 or 3 pages, very readable. So please, I encourage you to read those before you look at the next assignment. Okay, so I will give you, so please read chapter 16, Blundell and Blundell, B and B, near the end of this chapter. So near the end. Okay, so this is all I want to say. Okay, so we can begin the next chapter. So the next chapter we want to apply. We learn to look at a very spatial case. So this is we have two chapters on the application of what we have learned so far, from first law all the way to all these thermodynamic potentials, Maxwell relations. Okay, so two chapters. This one is the first of the two. We are going to look at the phase transition. And the next chapter, we are going to look at a non-PV system. So we are going to look at a wire, the thermodynamic of a wire, and the thermodynamic of a magnetic system. And there we are going to talk about how to do cooling. And we will take that chance to introduce the third law of thermodynamics. Okay, so let's do this one first, phase transition. The question I keep asking is the following. So I'm going to ask again. So this is the key question. How do we know? How do we at least show that? How to at least show that our second law, which is something really new, right? So how do we show that the second law is correct? Okay, you develop all this notion of second law from looking at engines. Okay, so you look at the heat engines and then you look at the Clausius inequality, and suddenly you get this new function of state which you call entropy, and then you use it to look at reversible, irreversible system, and so on and so forth. And then still the feeling is, how do we have something which we can appreciate more readily? Okay, this is perhaps more personal view, my personal view. Okay, and I will look at it this way. I will view it as I will view phase transition as a good proxy for you to understand, to at least feel that the second law is not crazy. Okay, so you can look at the phase transition. Why do I say that? The thing is, you do all this engine treatment, but okay, I am trying to teach you thermodynamics based on all these heat engines, but even myself, I have never built a heat engine. Okay, so that is unfortunate. I would like to go and really build one and then tell you, this is correct, so don't worry. But phase transition is something I do all the day. I know how to boil water at least. Okay, so this is something you also know how to do, and therefore this is a good proxy for us to really appreciate the beauty of all these laws that we have developed. Okay, and just some terminology, but before that, let me look at this question. There's a question. Okay, you have a question. Can you ask the question now? Student Wu. Okay, please type the question, and I'm going to continue writing, and I will answer when you finish. Okay, I encourage you to ask question right away, because you will say page 7. You even know your question. You even know which part you want to ask. It's much better to ask right away. Okay, so I'm waiting for your question, and right now I will continue writing. So for those of you who are watching video, you might not see the chat. You don't know the question, so I'm going to repeat the question for you. There's a question about page 7, which is coming up. Okay, so I'm going to flip back to answer those. Okay, so I'm going to look at a very standard case, which we will have gas, liquid, and solid. For the purpose of this part, you can imagine you are looking at H2O. What I'm going to analyze is a pure substance. So what I'm going to examine in this lecture, in this chapter, is how this H2O can have different phases. Okay, and what happens when you have the coexistence of two phases? So what I'm going to use the word pure substance. So this is the meaning of pure substance. Don't be confused. Now, pure substance doesn't mean pure phase. Okay, so we are going to use phase to denote. Now, these are the three different phases, but they are the three different phases of the pure substance. This is the scenario we want to analyze. Okay, so here we have gas. The terminology is when we have gas transforming into liquid, we call this condensation. Okay, and then from liquid to solid, we call this freezing or fusion. And this is less common. You can go from solid to gas directly. That is called sublimation. Okay, for example, if you have if your pure substance is carbon dioxide, CO2, you know how to do this. You maybe have done it a lot in shows or performance. You can have solid carbon dioxide going directly into the gas phase. And I also do not want to bother with the distinction between vapor and gas. I would just assume them to be the same. Okay, it's not that necessary to really distinguish too much about the two. Okay, and the reverse process, we would just write this out. So from liquid to gas, we have evaporation. Okay, and this you know very well, this is melting. And then this one, if you go from gas to solid, this is the reverse process. So you have the sublimation. Okay. So what we have, if we look at these three phases or three states of matter, there are more, but we look at this to build the thermodynamics. We know we need to compare the particle distance, the spacing between the particle. And we want to compare these two length scales. Okay, so a meaningful length scale is we look at the size of the particle and the spacing. Okay, so it's well known to you that if I have a gas, this is what we have. Okay, and if you go to liquid, you begin to shrink the particle distance significantly such that they are almost the same. Okay, but still, this is not enough for us to characterize our gas and liquid. And these are not the full story. We need something else. We need to look at the motion of this particle. So here, the particles almost move randomly. So here, particle also move randomly, but to a less extent. So this is also the case, but to less extent. Okay, and finally for solid, we can fill in this table quickly. So here, solid and liquid, they are quite similar in terms of these two length scale, the comparison between the two length scale. Okay, so the particle spacing is similar to the size of the particle, but here you have ordered phase. So the particles are ordered. Okay, so they are pinned to a real space coordinate. They can vibrate about the equilibrium position, but they cannot move randomly anymore. Okay, so these are the crude classification. Okay, let me look at the question. Okay, now let me read the question. So the question is, about 7, right? Here. So this is the question. Again, I understand those watching the video might be lost. So this is the question. Okay, do we choose the constant P because S is not decided by pressure, so we can choose P at the constant at P at constant as the condition. So here, this is look at this just mathematically. Okay, so this question is about this line here, from here to here. Okay, so from here to here, when we learn how to manipulate this partial derivative, we know we can do this operation, right? We can introduce, let's say I have this line here. Okay, suppose I know T and V are controlled by another parameter, let's call U. Then I can ask myself, what is now suppose I know T and V are controlled by U, right? Unknown parameter, right? Then implicitly my S will be controlled by U as well. Okay, then I can write down this line. I don't want to copy this again. Plus, this is this guy here. Okay, so 1, 1, 2. Okay, so this is the meaning of this line. Okay, but if you write it in terms of partial derivatives, you need to then ask yourself, is there any other variable that you have to keep constant? Okay, if you do, then you have to put that in, right? That will be this variable here. Okay, so here, this is what I choose to write down, which is more sensible thermodynamically for us to analyze the situation. So I'm going to let the change be driven by temperature. Everything is driven by temperature. Temperature will affect my volume. Temperature will affect my temperature, and temperature will therefore affect my entropy. And I'm going to do this by controlling the pressure. Okay, so that is why I have this line here. And in fact, I didn't say too much. For the partial derivative, there are many things you can do. You have known all the basic. You can manipulate a lot of situation, and this is a way where you change variable. Okay, so suppose you have a function of x and y. Suppose you have a function of x and y, and then you further know that x is a function of t, y is a function of t. Say t is the time, right? Very easy to imagine. I have a function which is I have a function f, which is a function of spatial coordinate x and y, and x and y can change with respect to time. Then I will have a line like this. Okay, so I hope this is good enough for this answer. Okay. So here I will keep it here. I will keep it here. Okay, I will keep it here. Now you can have other things. They are constant. You can choose other things, but are they useful? Maybe not. Okay, you can kind of think of this as now this is an example from Blundell and Blundell. You can kind of think of it as these few lines are designed for proving this. You need to prove this equation here. How do you do that? So if you want to do it this way, then you have to think of a good differential to manipulate. And this is a good one to use because then I can get my C sub P. Okay, and how do you do things like this? How do you know this is the things you the partial derivative you need to use? You need some practice and you need some common sense, and that is why you need to you're invited to read these pages. Okay, so for example, inside these few pages, there's one important line that which I like. You say when you manipulate all these partial derivatives, you always need to try to identify a heat capacity. Okay, because this is something you can measure in the lab. Right, so if you look at this partial derivative, right, the change of S with respect to T, a constant whatever, and if you read this, Blundell and Blundell suggest that you should try to recast it into heat capacity. And how do you do that? You multiply by T. So this line here is actually aligned with one of the tips given by Blundell and Blundell. Okay. All right. So now the last question I want to answer quickly again is a question from your classmate. I will read it. It's related to what I wrote here. Okay. So can we write f of xy as a function of f of t? Can you simply write it this way? I would say this is not a good advice if you want to start from the function of two variables and look at these partial derivatives, because if you do it that way, if you write f of t, you kind of lose all the information. Okay, so the reason, of course, in the end, this is controlled by t. That's why you can have partial f, partial t on the left hand side. But you lose all the partial derivative, which tells you how x of t, how x varies as a function of t and how y varies as a function of t. So I would recommend you to keep all these lines clear. Okay, so you can. This is one way of playing with partial derivative. You can imagine more complication. I can also have. I can also change a variable from xy to uw. Okay, and then if you want to change the variable from xy to vw, you need to learn more about how xy related to v and w, and there you have more partial derivatives. Okay, now this is should be in a standard mathematics course. They will teach you how to deal with this kind of situation. But it's just maybe sometimes people don't appreciate that much, and in particular in the context of thermodynamics, sometimes the symbol are not as clean as when you deal with x and y. Okay, so but if you look at mathematics, this line is true, it's correct. Okay, can I move on? All right. Okay, so where what did I talk about? I stopped here. So because of all these questions, we don't have time for break. No, I'm only joking. It's just we will have a shorter break. All right. Now we'll talk about continue to talk about phase transition. Okay, my slides are all messed up now. Okay, I will use here. It's a comment here. You can have more than one solid phases. Okay, so even if you have the same substance, if you have a pure substance can have a pure substance can have multiple solid phases. This is actually very common. If you think about ice, you might not, if you think about H2O, you might think this H2O, the ice in your iced coffee is the only solid phase. But that is because you are too used to ice, water ice. But let me very quickly give you an example. This situation is called polymorph. Imagine carbon. Carbon, you have diamond, or you can have graphite, you can have graphene, and you can have all these solid phases. Okay, so it's this is a comment that you should keep in mind. And the other thing, another comment is we are talking about this kind of gas to liquid, liquid to solid, and solid to gas phase transition. But what we develop here can also be used to understand other type of phase transition. Okay, so we can have other phase transitions. Okay, the common ones are if I have solid phases, I can have a phase transition from one solid phase to another solid phase. So that is why solid state physics is very rich. There are so many different possibilities, and if you take the solid state physics course, you will see you can have a structural phase transition. For example, you can have one structure at high temperature, but when you cool down, it changes to a different structure. And these different structures, different solid phases might have different functionality. You might be able to functionalize it for different purposes. You can make devices, you can choose the correct structure you want to make to suit the purpose. Okay, so that is why this is a very big research area. Okay, so structured transition is easy to imagine. And I can also have a superconducting phase transition, which is something I handle in my group. We deal with this on daily basis. For example, you take a piece of metal, you cool down to a low temperature, and suddenly no more resistivity. And then you can also have a magnet. Like imagine your the magnet on the fridge. And this is called a ferromagnet. If you happen to warm this piece of magnet up, you cook it to a very high temperature, it suddenly becomes non-magnetic. Okay, so these are other phase transitions that we can imagine, and they are also important for us. A warning is this phase transition I listed here. There are many. I can also have a phase transition, some electronic phase transition into more exotic electronic phases. For example, some kind of charge density wave, spin density wave, and so on. What I want to say here is all this transition, not all of them are first order transition. Okay. And in this chapter, we are only going to talk about first order transition. So here, this chapter, the major part of this chapter, if you see my notes, you will see the major part deals with first order transition. And also, we are going to look at only the pure substance and pure substance. And towards the end of this chapter, we are going to look at higher order phase transition. Now, I know some of you might already scratch your head. What do I mean by first order? I will explain soon. Just bear with me. Let me finish writing. Okay, and pure substance. So pure substance means I'm not gonna be bothered with the case where you put H2O with oil, that kind of substance. So I'm only going to look at H2O, for example, and then I'm going to analyze just the H2O using this kind of phase diagram. Now this is a phase diagram, generic phase diagram. You can already see with 3 phases. With a pure substance, we can already gain a lot of rich information. Okay, so pure substance, maybe let me be a little bit more accurate. This is a substance with uniform chemical composition. Okay. Now, a few words about first order transition. First order transition means when you look at some quantity, if that quantity is the first order differential of some energy function, that quantity will jump at the phase transition temperature. Okay, so let me say this again. We are going to look at some differentials. Right, we know, for example, how to write the volume in terms of the derivative, right? I told you once you know all this thermodynamic function, this energy like quantity, you take appropriate derivative, you get your volume, for example. Okay, so volume turns out to be a quantity that will change, will jump at the phase transition temperature. Okay, and this volume is the first order differential of some energy like quantity. And therefore, if you detect a volume jump at the phase transition temperature, this phase transition is classified to be first order. Okay, there are some transitions that will not have this. When you undergo a phase transition, there will be, for example, entropy is another one. Entropy will change, but it will not jump. So by jump, I really mean jump. Something just jump. This is jump. Okay, so I can also have the situation where this quantity only show a king, but there is no discontinuity. So that will be called a higher order phase transition. Okay. All right, so this is a good time to take a break, and then we are going to look at this diagram. So let's keep this break short, just enough to go to a bathroom. Okay, so come back in 5 minutes. I'm going to start at 12:45. Okay. Welcome back. Let's continue. Okay, let's quickly look at this complicated 3-dimensional 3D phase diagram on the right. And here you have 3 axes. You have P, V, and T. This is a generic one, which means you do not really see all these numbers given. Okay, so it's just a schematic, if you like. Okay, so this is from, I took it from Atkins, your textbook. So I hope you can see well that there are two kinds of lines here. One is thicker, the other one is thinner. Okay, so for example, there's this line here, G, starting from G. Okay, you go up G, N, C. So G, N, C, O, F. So these are thick line, right? So this thick line tells you phase boundary. So these are phase boundary. Okay, so at the phase boundary, if you have a boundary, so on one side of the boundary, you have one phase, on the other side of the boundary, you have the other phase. And so phase boundary is where the two phases coexist. Okay, so this is phase boundary is where phases coexist. Where phases coexist. Okay, important. This is important concept. We are going to use it soon. And then here there's a critical point C. So this C is a critical point. Okay, you can see beyond the critical point, if I'm on this side of the phase diagram, this side, there's no way to distinguish between gas and liquid. Okay, so this is a critical point. And then here, let's look at one of the isotherm. The isotherm is shown here as a cut, right? So you cut along the constant temperature axis. So if I cut at the temperature below TC, critical temperature, I will have, let's say if I look at T3, right? So I can see when I'm at large volume, this is the vapor phase. Okay, so if I change the pressure a little bit, I will be able to compress. I will be able to compress the volume quite quickly. Okay. And then when I reach O, I enter the so-called liquid and vapor coexistence line. So in this region, inside here, I can have liquid and vapor. Okay, so I keep the temperature constant. Now suppose I reduce the volume. If I reduce the volume, I will have more and more liquid and less vapor. But the pressure will not change too much. Okay, and if you put it the other way, you can think of it this way. This line is almost horizontal in the PV diagram. What does it mean? It means if I change the pressure only a little bit, the volume will change a lot. Okay, so this is due to the fact that we have vapor. The existence of vapor means this system is very compressible. Okay, and using the same argument, you can try to understand why after you reach the other phase boundary and on the isotherm, which means on the PV diagram, you do a cut, isothermal cut, you have very steep line for the liquid phase. That is because you have to, if you want to change the volume only by a tiny bit, you have to change the pressure a lot. Okay, that is because you enter a phase which is less compressible. And you know about triple point, and here you can have the triple point is where the solid phase, the liquid phase, and the vapor phase can coexist. So this is the triple point. Okay, so this is rather complicated. So usually we like to look at the projection. So these are the projections here. I already kind of discussed this one, the projection on the PV diagram. You can think of it as here the isotherms are shown here. It's a little bit more messy, but you can I'm sure you can appreciate how to do this cut. And more commonly, we use the PT diagram, the projection onto the pressure temperature phase, the pressure temperature plane. Okay, so if I draw it for you schematically, you will have something like this. So here, now this C again is the critical point. So this C is a critical point. So if I draw it, I will draw the P versus T for you. The standard one is this. You have coexistence line, phase boundary, which is the coexistence line that goes like this. Okay, so between liquid and gas, you have this phase boundary up to a point, critical point. So this is the critical point. Okay, and beyond which you cannot tell the difference between liquid and gas. Okay, and then you have another steeper line here, which tells you the phase boundary between liquid and solid. Okay, and for water, this line is slightly different and might not be too difficult for you to already think about why this line has a slightly negative slope. So this is water. Okay, so for H2O, this line is a little bit, a bit of negative slope. Okay, and why? Okay, now I want to give you some experimental observations. So here I'm going to give you the this is what we observe experimentally, or experimental facts, if you want. Okay, one, if we measure the heat capacity at whatever under whatever condition. So let's say we measure the heat capacity measurement. This is what we will see. We will see. Now let me define it first. We already saw something not long ago. So heat capacity is the partial derivative with respect to temperature at some constant criteria X. Okay. And let's say if I go ahead and measure this, I can measure it at constant pressure. Right? This is the easiest one for me to imagine. So this is a situation. You will have, let's say I start from some temperature not too far away from the phase transition temperature of liquid to gas. Okay, so I'm talking about boiling point. So I will take the measurement. I will take heat capacity, and at some point suddenly I see a huge jump, a sharp jump, and then it comes back down. Okay, so theoretically this goes to infinite, but then when you do experiment, you never go to infinity. You will get a sharp jump, and then it comes back down, and then you get a more reasonable value. Okay, so this is liquid, for example, liquid to gas. This is my boiling point. I will call it T star to denote the phase transition temperature. So this is one of the experimental fact. And second, the other bit we know is this. We know if you have a phase transition temperature, you need to supply additional heat right at the phase transition temperature. Okay, and that amount you supply is called latent heat. It depends on which direction you go. Okay, but in general, there will be more heat needed. Okay, more heat energy involved in this phase transition. So this latent heat is called L. Okay, so, and you know you have to supply this heat at this temperature T star. Okay, you have already learned enough thermodynamic to see that this cannot be an equality. This is heat energy. This is temperature. So to complete this equation, I must bring in some other stuff, and that turns out to be the entropy change. Okay, change between what? Entropy change between the two neighboring phases. Okay, so you can also think of it as the entropy. I already provide you an entropy scale. I have a way to choose a fixed point. Okay, so this part is something related to the third law. But in general, this is if you have the same fixed point, they will disappear once you take the difference. Okay, so here you have phase 1 and phase 2. What happens really? What happens is you can look at it this way, right? You can look at it like I can use some condition to drive it across the phase transition. Let's say from liquid to gas like this. So I'm crossing this line. This is a phase boundary, and this phase boundary right now is characterized by a single parameter T star if I keep the pressure constant. Let's say I keep the pressure constant. Okay, this one here, C sub P, right? So in this case, I'm traveling horizontally here. And what we say is phase 1 and phase 2 are in thermal equilibrium at T star. This is the terminology. Okay, so if I draw, let me draw this diagram for you, the second experimental observation. Yeah. Again, very near T star. I'm going to put my T star here. Now I can expect this kind of situation. What happens is this. Let's say again I'm in the liquid phase. I will have some entropy, right? When I increase the temperature, I will have more freedom to explore. Okay, so this one will go up a little bit. Right, so this is the value of S1 here, right at the T star. Okay, so at T star, I will have another entropy S2, which is associated with this jump. And what is this S2? S2 will be continuously linked to the entropy in the other phase, say the gas phase. Okay, again, it will increase a little bit, but maybe the amount is different with a different slope. So I'm going to schematically draw it like this for you. Okay, so this is what you can expect. That is to say, if you detect a latent heat, the latent heat is related. If you detect the latent heat at T star, this is T star, it must involve the change of entropy. So this is another thing that jump. Okay, and this entropy you recall is the first order differential of some energy like quantity, right? So this is a characteristic of first order transition. Okay, so this is an experimental observation. Now the last piece that I would like you to really synthesize the knowledge together is actually these two are consistent. Okay, so I told you, I presented this as two independent experimental facts, but actually they are related. Why? Look at this. What is this heat capacity? If I have the latent heat, I told you it has to be associated with a jump in entropy like this. Okay, and then and here this is how you calculate the latent heat. This is the latent heat. This is this jump is related to L divided by T star. T star you can read from your device, from your measurement device. Okay, and if you have a jump like this, a step function like this, if you take the derivative, you must have a singularity. That is why your heat capacity is the first derivative, right? And therefore you should have a diverging heat capacity. So this is consistent. And put it a different way, what is the quantity that is easy to measure in the lab? The quantity that is easy to measure in the lab is the first one, right? So heat, if I have a good meter, I can also do it, but the heat capacity is something standard in the lab, which we can do. So what I should do is to look for this kind of feature, and I will be able to tell that there is a phase transition happening, and more importantly, I can say something about the order of the phase transition, whether it's first order or higher order. Okay, now and then the next part, let's build upon this and look at this figure here. This is the figure from Blundell and Blundell. I kind of like this figure because it's very quantitative. All these numbers are very realistic. I checked several sources and they are very accurate. Okay, so from here you can see what happens when I have liquid to gas phase transition for H2O. So this is H2O. So here, according to what I say earlier, you will be able to say something about the heat capacity, right? So here, what is the heat capacity? Is the slope of ST curve. So let's look at the ST curve. Where is it? If you look at the ST curve, I will be able to look at the slope and tell something about the heat capacity. And from here, I will be able to say, okay, the heat capacity of H2O in the water phase is larger compared with the gas phase, at least in the vicinity of the phase transition temperature, right? Because there T, you have this T times the slope, but the T doesn't change too much, but the slope is more obvious here. Okay, and indeed, this is something you can easily check. You can look up the textbook, and I provide the number in my note, and this is indeed correct. Okay, so here the heat capacity is 75 joule per Kelvin per mole. So this is in the liquid phase. Sorry, this should be drawn here. It doesn't matter. Let's forget about this line. And in the gas phase, it will be 34. Okay. Now, because this is so realistically drawn, I have designed an assignment question based on this figure. And just a reminder, when you do this question, please be as accurate as possible and read this. I want some quantitative analysis of everything. And you'll be able to get, well, in my opinion, it's something rather satisfying when you get all these numbers. You'll be able to get consistency and to show that everything we developed so far is logical. Okay. Our aim is to learn how to describe the phase transition, this line here. Okay, so the phase boundary is something I want to learn how to describe, and through that I will learn something else. Okay, so let's make it a bit clearer. What is my goal here? My aim. My aim is to derive the phase boundary. So I want to derive the phase boundary on the PT diagram. That is to say, I want a function P as a function of T. I want that function, so I can draw the phase boundary. Okay, what is my strategy? So the strategy is this. The strategy is to look at dp dt instead. Unfortunately, the most direct way is to get dp dt, the slope. And if I have dp dt, I want to get p as a function of t. Unfortunately, I have to integrate. Why unfortunate? Because you need to put assumption. So you need to integrate with assumption. Okay, and that will give you, if you put the correct assumption or reasonable assumption, you get a reasonably accurate phase boundary here. Okay, and how do I get this dp dt to begin with? I need to analyze equilibrium. Okay, remember, this is the line where the two phases are in thermal equilibrium. So I want to look at phase equilibrium. So this is the strategy from here to here to here. Okay, and this equation is a famous equation. This one has a name. This equation, you get dp dt equals something, right? So this is called the Clausius. Again, this Clausius has this name attached to almost everything in thermodynamics. This is Clausius-Clapeyron equation. Okay, so let me try it. Now, this part, I don't want to rush. It's very important. I'm going to look at this system. I'm going to imagine I have two phases of a pure substance. So this is, I will take a container and I will have two phases. Let's say I have M1, M2. The easiest one to imagine is I have a liquid phase coexisting with my vapor. Right? This is a simple experiment to imagine. So M, I will use the mass. I really need to introduce the mass. You will see why. So this is the mass, is the mass of the ith component or ith phase. Okay, to model this system better, I'm going to equip with a piston. Okay, what do I want to control? What I want to control is the pressure. I know the piston. I have the piston. That is something I know how to control. I'm going to idealize the system. I'm going to remove the friction, and that will be that will give me a way to control the pressure. And I can also control the temperature. So this is what I assume I can control. Okay, and therefore, if these are the parameter I can control, I can look at the system at a given pressure, at a given temperature. Okay, I can control it very well. I can choose one temperature, one pressure, and look at what happens. And then I choose another temperature, another pressure, and look at what happens. And that will give me a trace of dp dt. And put it in terms of differential, what I'm saying is I know dp is 0 and dt is 0. Okay. And now the question is, what is the next step? Once when we set up the problem like this, what is the next step to do? And this is a realistic system, right? I can, as I always say, we can imagine a beaker in the lab, and that will allow us to control the pressure. And I just use this piston to set the problem up properly. Okay, so if I know P and T, which thermodynamic function do I need to minimize? The one I need to minimize is the Gibbs function. Okay, what do I mean by this? I want to minimize Gibbs for the total system. Okay, which means M1 plus M2. Okay, this part is discussed in Atkins, your textbook. But I expand it a bit because students in the past got confused there. So I expand in a way that in the textbook doesn't say it that way. So I'm going to present a modified version based on my modification. Okay, so that's why please listen carefully. Okay, I'm going to minimize this. What do I mean? It means I want to minimize dg. I want to minimize g. So dg has to be set to 0. Okay. And what is G? And G, now this is more important than ever, that we need to be careful about this particular property of the thermodynamic variable. Okay, G is an extensive variable. If you halve the system size, if you have a homogeneous system, if you halve it, G will be halved. Okay, and the unit of G is Joule. Okay, this is the unit. So I'm going to write it as the Gibbs function for the first phase and the Gibbs function for the second phase. This is how I do the minimization. Okay. Now, why do I introduce the mass? If you think about it this way, later you get, okay, just keep in mind that we need to introduce the mass. Because this allows us to rewrite this in terms of M1 G1 plus M2 G2, where now these G's are intensive property. Okay, that is to say, the unit now, I will do the unit for you. So unit, okay, I will do here. This is in Joule. This one is in kilogram or gram, it doesn't matter, just the mass. And this will be energy per kilogram. Okay, now I can also use particles number, and there will be energy per particle. So you know this is an intensive specific quantity. Okay, now we are ready to do the minimization. So let's do the minimization. The minimization means dg is 0. dg is 0. And what is dg? dg is dm1 g1 plus m2 g2. And I will have m1 dg1 plus g1 dm1 plus m2 dg2 plus g2 dm2. That whole thing has to be 0. Okay. So now dg1 is 0. dg2 is also 0. And I have the next line here, which tells me I have g1 dm1 plus g2 dm2 has to be 0. Okay. So now the key here is, why is dg2 0? I would like some answer from the audience. Okay, right now I want to know why this specific case can be 0. Okay, so some answer will be good. And meanwhile, I will continue my treatment. Okay, what can I do next? The next thing is to understand this. Now, if I have so many kg of water turn into vapor, I will still have mass conservation. Okay, and you can see the way I draw this is kind of similar to the picture I drew when we discuss availability, right? I have a conservation of mass, so I have a conservation law. So the conservation of total mass means this m1 plus m2 has to be a constant, right? m1 plus m2, they cannot create mass, so this has to be constant, so the differential has to be 0. And therefore I have dm1 is minus dm2. Okay, then I can plug this in. I will have g1 dm1 minus g2 dm1, right? dm2 is minus dm1. This has to be 0. Okay, but we do not assume this to be 0. Then there's no phase transition. There's no coexistence here, right? So this is this conservation tells me we will have to set the specific Gibbs function to be equal as the phase boundary. So this is a key result. Okay, so if I go and look at all these phase boundary here, so if I pick this point, what do I know about this phase boundary? What I know about this phase boundary is the specific Gibbs function has to be identical for the two neighboring phases. Okay, so this is the key statement. And now it's your turn. Why can I set this DG1 and DG2 to be 0? Come on, give me some feedback. Okay, nice answer. Okay, I want to do it really properly because the next part requires this. Okay, so I'm going to give you the differential form of the Gibbs function. So the change of dg is governed by this, right? S dt plus v dp. Okay, now here I'm going to bring in this knowledge. If I have now this g, I told you capital G is extensive, so I'm going to use this symbol. Okay, what are the extensive variable here? So we go to this equation. Now this is what you learn. The equation I just wrote down is what you learned before. Okay, but I think that we should really be careful to label which one is extensive. So this is extensive. This is extensive. Temperature is intensive. And pressure is also intensive. Okay. So my claim is this: if you have a product of two variables, if you have intensive times intensive, that's okay. If you have intensive times extensive, that's also okay. Now you might want to think about this remaining situation. If I have extensive multiplied by extensive, this is not okay. Not okay. Okay, so keep this in mind. We are going to use it to look at a different thermodynamic potential functions on Wednesday. So let's complete this one because this one is we are nearly done. So if you do it this way, this is extensive, right? On the left-hand side is extensive. For completeness, let's complete this. So this is extensive. G is extensive. Okay, now how do I create this intensive times intensive version? I look at the specific case. So I divide by the system size. So if I divide by the system size, this becomes d little g. And you have to choose a variable which you can do this operation. Okay, and if you divide by the system size, it's naturally if you divide this the whole thing by the system size, it's naturally valid to choose the extensive variable to do this operation, right? So I will have s little s times dt. Right? If you do temperature divided by system size, this doesn't give me new insight. Temperature per particle, what is the meaning of that? Right? But entropy per particle is completely meaningful. And likewise, what is the meaning of pressure per particle? I don't know, right? But if I look at volume per particle, that is reasonable. What is volume per particle? V divided by M, you know, because this is related to the inverse density. Okay, so I will also choose volume to do the division. So in this case, I successfully generate this line for you, which have intensive multiplied by intensive. And then likewise for here, and likewise, this is intensive. Okay, and now T and P are constant. So dP and dt are 0. And therefore, my dg, lowercase g, will be 0 for both of these. Okay? And now you should be very careful, because here, this line is correct. dg is 0. This is what I want to minimize. But then once I write out the component, this is the way to do the analysis to get the correct answer. Okay, why is this important? If you read Atkins, Atkins doesn't have this analysis here, the intensive, extensive. This is something I add because I want to look at the next case here. So I will phrase it for you, so you get a chance to think about this. So now, let's say if T and V are known and controllable, let's say you can control this, right? So in this case, I will have dt and dv to be 0. So what is the equivalent condition at the phase boundary? Okay, so now here's the case. If I have this, if you look up the table I showed earlier, you will say, I know, I control T, I control V, and they are naturally, I need to minimize the Helmholtz function F. So I have to minimize Helmholtz function F. So I repeat all the analysis, and this analysis will be parallel to what I did for constant T, constant P. So I can conclude that the specific Helmholtz function has to be the same. Okay, so this is something very wrong. This is something very wrong. And this line remains correct. Okay, and why is this wrong? This is a good topic for Wednesday, right? So this is the preview. I'm going to do this analysis, and I'm going to really examine carefully whether a particular thermodynamic variable is intensive or extensive, and tells you which operation is not allowed, and therefore now it's very common to lead to this conclusion of F1 equals F2 because there's one argument which is wrong, and which argument is wrong, that is the same. If you are not careful, you wrongly conclude that dF1 is 0 and dF2 is 0, and everything is parallel. Then you will just get F1 equals F2. So this is also wrong for this case. And to see why, we will show it on Wednesday. Okay. All right. So thank you for staying with me. And that's the end of this lecture.